So the first thing we're going to look at is temperature and rate. So we already know that if you increase the temperature of a substance, it's going to make the molecules move faster. So if those molecules move faster, they're going to have more energy. If they have more energy, they're more likely to react. And we'll kind of talk about the factors that cause that to happen in a little bit here. You saw that visually when you put your glow stick in the hot water versus the cold water. So you could see right away as soon as you put it in there, it started glowing brighter to show that that reaction was happening faster. And we know from what we've done so far, K is temperature dependent. So if you increase the temperature, it's going to increase the K value. That's why you've been seeing those temperatures, even though we haven't used them until today. So what we can use to actually figure out the temperature or the activation energy or the K is something called the Arrhenius equation. So the Arrhenius equation shows us the relationship between the activation energy, which is how much energy is required to get the reaction going, and the temperature in Kelvin. So there's a couple different versions of this Arrhenius equation. This is one we're not going to use, but this has a couple different things in it that we're going to talk about. When you're talking about temperature and rate, there are things called the frequency factor and the exponential factor. So we'll talk about those in just a second after we just kind of do an overview of what activation energy is. So we've talked about activation energy before. We've looked at reaction diagrams before. So that activation energy is how much energy is required to get that reaction going. So you can think of it as like an energy barrier. You can think of it as reactants having to go up a hill to get to it, because a lot of times they'll use that visual of somebody pushing a rock up a hill so that the rock goes down the other side. So if that person can only get the rock to halfway up the hill, if he lets go, it's just going to roll back down. So the only way to get it to go over the hill is to get it to the top. So the same thing happens with your reactant. If the reactants only have enough energy to get halfway to the activation energy barrier, the reaction is not going to take place. It's not until they get to the top that they actually start reacting, and then you get your products. So this video is going to show two different reactions. And the other thing you can tell when you're looking at an energy diagram, and you'll see that difference in these reactions in this video in a second, is you can compare the energy of the reactants to the energy of the products. So if the energy of the products is lower, that means that it's released energy and it's an exothermic reaction. If the energy of the products ends up higher than where they started, then you know it's an endothermic reaction and they absorb energy. So the video is going to go through two reactions. The first one is going to be an exothermic reaction. The second one is endothermic. The first one is the methane bubble reaction that we do. So if you remember when we did that in here, you can put the methane into the bubbles, and the methane can sit in a room with all the oxygen in the room, and nothing happens until we light it, until we give it that energy to get it to the top of that energy barrier. So this will kind of help you visually see what goes on when that takes place.
If oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram will help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding, but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
Okay, so you can kind of see the difference where the first one, where it was below, and then the second one, it was above where the reactants were. So that kind of shows you the difference between endothermic and exothermic. So when you're looking at that energy diagram, there's a couple of different things you can see. So we already looked at the reactants versus the products. So the reactants are here. In this particular example, the products are below. So would this one be exothermic or endothermic? Good, that one's exo because the products have a lower energy value. So if you know the actual values, you can calculate the overall energy change. So for this one, if this is exothermic, would that energy change be negative or positive? Negative, right, because you're releasing. Okay, the other thing you can tell, again, if there were values here, is you can figure out what the activation energy is. So the activation energy is the difference between where the reactants are and the top of that energy barrier. Also, at the top of the energy barrier, if it shows you what the progress of the reaction is in terms of the actual substances, you can see what's called an activated complex or transition state, and that shows you an intermediate that forms that's pretty much unstable as you're going from the reactants to the products. So it's not going to show up in the overall equation, but it's kind of those reactants and products transitioning from one to the other. And then again, like we said, the activation energy barrier is that difference between the bottom and the top. A couple other things we can look at are the frequency factor and the exponential factor. So the frequency factor is how many times those reactants try to get up that hill. And then the exponential factor is how many of those approaches or a fraction of those approaches are actually successful. So you won't have to really do anything with those two terms because we're not going to use the form of the equation that includes those. But if you were, those values would have to be given. Also, again, to pull back on that temperature, the exponential factor, so how many of those approaches are successful, are going to increase if your temperature increases because you have those particles are moving faster and they have more energy, but then it's going to decrease if that hill gets higher. So if that activation energy barrier gets higher, then it's going to decrease. Okay, this particular visual is, I won't put this on this test, but this is just something that you might see again, so I like to talk about this a little bit. This is just another way to visualize what happens as you change the temperature and how those molecules are able to deal with that activation energy barrier. So if you think about that diagram we just had, it's almost like taking it and moving it this way to where now this is the activation energy barrier. So what this is showing is what fraction of molecules are able to reach that activation energy barrier based on their temperature. So at a lower temperature, you can see that there's more molecules to the left of the barrier, but as you increase the temperature, it kind of flattens out and you get a larger fraction that are able to have enough energy in order to react. So if you look at that top diagram, you can see that as that temperature increases, how it flattens out and you have more substances that are able to react. Okay, this is the form of the Arrhenius equation that we're going to use. So what this would allow us to do is to figure out either the activation energy given the K's in temperatures from two different reactions, or it would allow us to figure out a K value or possibly a temperature. So the example we'll do is to solve for the activation energy, but you could be asked to solve for something else. So when you're doing this, K is going to be the rate constant. So you would either have to have already figured that out or that would be given. EA is the activation energy. So again, how much energy is required to get that reaction going. T is temperature, but it has to be in Kelvin. And then R is the gas constant. It's the same gas constant we've used before, but it's in a different format. So this time we're using it in joules per mole Kelvin. So that's going to, when we solve for EA, that's going to give us the activation energy in joules. Okay, so here's an example. So again, we're using the equation ln K2 over K1 equals activation energy over the gas constant times 1 over T1 minus 1 over T2. Okay, the other thing you might want to write down here, because if you're going to be asked to solve for K2 or K1, you're going to have to manipulate that natural log expression. So if you remember from math, if you have the natural log of something over something else, it's the same as the natural log of the numerator minus the natural log of the denominator. So we won't need that for this problem, but if you're being asked to solve for one of the K values, you'll have to use that to get rid of that natural log. So I would write that kind of off to the side in the box so that you have that. Okay, so for this one, we're going to go through and make a list of what we have here. So we have T1, and it's already in Kelvin. And then we have a K value that's associated with that temperature. So that's our K1. And then we have another experiment at a different temperature. So this was at 895 Kelvin. And this K value was 567 and to the -1 S. So the R is going to be a constant. So that one's always going to be given, and you'll always have that. So 8.314 joules per mole K. And then what we're looking for is the activation energy. So we'll sub those values into our equation. I'll show you kind of step by step what the math looks like. So if you get stuck or you don't get the right answer, you can kind of go back and see where you. This is a constant. So that's that gas constant. So anytime you do one of these, that value would be given.
Okay.
Yeah. And when you solve this, the energy is going to be in joules, but these are typically reported in kilojoules. So you wouldn't necessarily have to, but that's how we're going to report it here. Okay, so try the math on that one. Make sure you can get that to work out. The last calculation. So the rest of this is basically conceptual things. So thinking about what is actually happening to the molecules that can affect that rate of reaction. So when we're talking about reactions taking place, we look at something called the collision model. So we already know from previous units that when a reaction takes place, you have to break bonds in the reactants and then form bonds in the products. So in order for that to happen, the only way that this can take place is there have to be three things that happen. So the molecules not only have to run into each other, they have to collide in the correct orientation. So they have to hit each other in the right positions and with enough energy to cause those bonds to break and the other bonds to form. So the two examples here, you can see in this first example, you end up with the same substances. So those three things did not take place. But in the second reaction, it did. So you can tell if a reaction has taken place if you've had new substances formed. When you're looking at this collision factor, you can look at something called the orientation factor. So this represents the fraction of collisions with that orientation that allows the reactions to occur. The other thing we can look at is something called the collision frequency. So it's the number of collisions that occur per unit of time. So if you think about these things, again, if we think back to temperature, this is why temperature increases the rate of the reaction. Because if the temperature increases, the molecules are going to be moving faster. The faster they're moving, the more they're going to run into each other. So the more likely they're going to hit in the right position, the more energy they're going to have, and the more likely they're going to be just to run into each other in general because they're moving faster. Again, another example here. So you can see those first two, when the oxygens hit each other or the oxygen and the chlorine hit each other, those are ineffective collisions. But when you have the nitrogen or the chlorines and the fluorines running into each other, then you have the effective. Okay, so next thing is looking at reaction mechanisms. So we've talked about reaction mechanisms before. We've looked at them at least when we do Hess's law. So when you look at Hess's law, it gives you those steps that you add up to give you the overall reaction. So those are the reaction mechanisms for given reactions. So it shows us the steps by which an overall chemical reaction occurs. And those are called elementary reactions or elementary processes. We also have dealt with reaction intermediates before, even though we haven't exactly called them that. So those are the things that are produced in one step of a reaction, but then cancel out or get used up in a later step, and they don't show up in the overall equation. So a reaction intermediate is something that forms in one step. So you first see it as a product, and then it becomes a reactant and gets used up. When you're looking at a reaction mechanism, you can identify each of the steps by what's called their molecularity. So this tells us how many molecules are involved. So this is a little different because it's not just how many different molecules, it's how many total molecules. So if something only has one reactant, we call that unimolecular. If it has two molecules that have to react, and this could be two of the same, or it could be two that are different, we call that bimolecular. And intermolecular, these are not as common, again, because think about, instead of just having to have two things that collide, now you have to have three different things that collide with the right amount of energy and the right orientation. But again, three total, so not three different. So it could be three of the same thing, it could be two of one and one of something else, or it could be three different ones. So again, when you're talking about molecularity, you're talking about how many individual molecules are in the reactants of those particular intermediate steps. This is an example we used before when we talked about kinetics a little bit in honors. So anytime you have a multi-step product, multi-step process, one of those steps is going to be slower than the others. The slow step is always going to be the rate determining step. So at this level, you don't have to be able to identify which one is slow versus fast. But if they're labeled slow and fast, you need to know that the one that's labeled slow is the one that's going to determine the rate. So the example we've used before is driving from here to the mall. So if you break it down into three steps, first step from here to the bridge, second step getting across the bridge, third step from the bridge to the mall, almost always this is going to be your rate limiting step. So it doesn't matter how fast you can get to the bridge or how fast you can get from the other side of the bridge to the mall. If there's traffic on the bridge, that's going to slow your overall process down. Another visual example that's sometimes used are the funnels. So if you think of this as a three-step process, wherever that small funnel is, that's going to slow that whole process down. So that would be the rate limiting step. We can also look at energy diagrams for these multi-step reactions. So every time you have a step, you have a new activation energy. So there's a couple things that could be asked about one of these diagrams. So the first thing to notice is that the activation energy always goes from where the reactants are to the top of the activation energy barrier. When you're looking at the next one, it goes to where the reactants previously stopped to the next activation energy barrier. So when you're looking at a multi-step reaction to look at the activation energies, you look at where it was previously before it had to overcome that energy barrier. The overall energy of the reaction is still the difference between reactants and products. So again, what kind of reaction is this one? Right, this is also an exothermic one. You could be asked, how many steps does this reaction have? So you would just count how many activation energies are listed on the graph. And then you could also be asked which one determines the overall rate. So again, when you're looking for the slow step here, how would you know which one is slower? So the one that has more energy or that takes more energy, that's going to be your slower step. So the larger the energy, the more likely it is that that's going to be your slowest step. So those are a couple things that could be listed or could be asked on an energy diagram. Okay, so here's an example of a mechanism. So this example is not in your notes, but just so we can kind of talk through what some of these things are. So this is your mechanism, and it gives us this labeled slow step versus fast step. So you can see NO3 as an intermediate because it's produced in this step and then used up in the next step. Now, when you have an intermediate, it doesn't have to be used up in the next step. It could have been used, like if there's more than just two steps, it could be used up in step 3. But you have to see it first as a product, and then it becomes a reactant and gets used up. If you have a catalyst, which we'll talk about in a minute, a catalyst you would first see as a reactant, then it would show back up as a product. So those are the two things you'll have to identify, are the intermediates and the catalysts. And then you can see on this one that CO is not involved in the slow step or in the rate determining step, so you're not going to see that appear in the rate form. All right, lesson on catalysts, and this kind of ties in. So we can also look at catalysts or catalyzed reactions on those reaction diagrams. So what a catalyst does is it increases the rate of the reaction by decreasing that activation energy, and it can also give it an alternate pathway for that reaction to occur. So when you're looking at a catalyst, there's two different types. Homogeneous means the catalyst is the same state as the reactants. So if you have aqueous reactants and your catalyst is aqueous, like when we do the elephant toothpaste, we use a homogeneous catalyst because it's an aqueous catalyst. Or you could have a heterogeneous catalyst where it's a different state. So a lot of times catalysts are solids, and we'll see a visual of that in a second and kind of explain how that works. So when you're looking at a diagram for a catalyzed reaction, one thing to notice is that the reactants and the products are always in the same place. So even for a catalyzed reaction, the energy of the reactants and the energy of the products are the same. The only thing that's different is the activation energy. So you can see how this particular one, instead of it happening in one step, it gave it a multi-step reaction. And the other thing you could see is you could see it where it still follows the same pathway and it's still a single step, but it just might be lower. So a catalyzed reaction is going to have a lower activation energy or it's going to have a different pathway. So this is our example of a solid catalyst. So a solid catalyst is useful because what it can do is almost give the reactants kind of a place to land. So it might hold one reactant in place, so the other one can then come to it and react. So instead of having two things moving around, you've got one substance that's kind of held in place. Or it might be a place where both reactants can land, react, and then leave that metal surface. So platinum is sometimes used as a catalyst. There's a lot of metal catalysts that are used. All right, last thing, I won't ask you about this on the test, but just to kind of tie in something you're familiar with from last year. So you talked about catalysts last year in AP Bio, if you took AP Bio, and biological catalysts are enzymes. So enzymes have that locking key model where you talk about the substrate, which is what binds to that active site in the enzyme, and then it reacts, and then they're able to release. And you guys probably did, the last hour said you didn't use liver for that lab you did, but you did a catalyst lab where you probably used potato. Remember doing that where it sped up the reaction. So liver does the same thing. Like you take hydrogen peroxide and you put a piece of liver in it. Liver has catalase in it, so it'll cause that hydrogen peroxide to bubble. All right, so next week we will do some demos with this. There's a couple demos we'll do with catalysts, with concentration. There's one where you'll actually be able to visualize the intermediate because it changes a different color. So when we review this stuff next week, we'll do some demos that go along with it. All right, last thing here is this last example problem. So this shows the decomposition of ozone from O3 to O2. And then the mechanism that's given is 2 steps. So the first thing we can do is show that that mechanism is consistent with the reaction. So just like we've done before, we're going to add this up and we're going to cancel out anything that we can before we add it. So we end up with 2O3, and then we're going to add the O2s together. That's where the 3O2 comes from. So then after we've done that, what would my rate determining step be? First step or the second step? Right, first step. And how do you know that? Or I'm sorry, not the first step. Right, second step, and it's the second step because, right, it's a slow step. Okay, so they will be labeled for you. You just have to make sure that you associate slow step, rate determining step, which makes sense if you think about it. What about intermediates? Is there anything that's an intermediate? Oh, good, because intermediate, again, is produced in one step, used up in another step. So you see it show up, and again, it doesn't have to show up in the very first one. You just have to first see it as a product, and then it has to become a reactant. What about a catalyst? Is there anything that comes in at the beginning and then comes back out at the end? No, so this one does not have a catalyst. Now, if you wanted to show what a catalyst would look like, if you want to add a catalyst, just so you can see, a catalyst would show up in step 1, and then it would come out in step 2. So if you added that, you could show that C would be a catalyst if we added that in.